Today, I'm going to explain you what integration is. First of all, I'm going to cover indefinite integrals, then definite integrals with bounds. So now you should know what differentiation is, d of dx. You should know this function and what it does before you embark and listen in this video. So let's say I have a function f of x, okay? If I were to differentiate this, let's say I get g of x, okay? So now there must be something I can do that brings g of x back to f of x. That would be awesome, right? So now there is actually something. It's called integration. Integration is actually the inverse operation to differentiation. It's the complete opposite. So if I were to integrate g of x dx with respect to x, basically, I get f of x plus c. This is known as it's an arbitrary constant and is known as the constant of integration. In this case, f of x, you see here, is known as the antiderivative. Derivative of g of x. Similarly, how g of x is the derivative of fx is the antiderivative of g of x. Simple. But what is this notation? Doesn't make sense. I think I can cover that in an example. So now let's say you know that d over dx of x cubed is 3x squared. This one we can use power rule, right? So now there must be something that brings 3x squared back to x cubed. So by using this formula we just got, I'm going to integrate, in this case g of x, right? It's 3x squared dx. It gives me x cubed plus c. So now, to understand where does this plus c come about, we must understand that if we were to even differentiate, say, d of dx of x cubed plus c, okay? And this c can be anything. It can be 2025, can be 5, can be e, can be anything. You know that when we differentiate a constant, it's just 0. So no matter what, we get 3x squared, right? So by that theory, if we integrate 3x squared, we get back x cubed plus c, and that c can be anything because there is infinite number of antiderivatives that differ by just a constant. So now a general formula would be the integral of fx dx is capital Fx plus c, where capital Fx is the antiderivative of small fx. This is what integration is. So this is the integration sign. This is the integrand, is the one that we're actually differentiating. Dx is just a constant. It's like we're the same way how we differentiate a variable with respect to x, we're integrating a variable with respect to x. We use the notation dx. This will make more sense when I explain in definite integrals, okay? So this is just the intuition of what integration is when there is no bounds. So in general, if we were to differentiate a constant, if we were to differentiate a variable, and if we integrate that result, we get back the same variable we got at the very start. and they differ by a constant of integration called c. That is what integration is. But now what exactly does it do? So now I will explain you using definite integrals. So now, let's see. We know that the integral of fx dx is capital Fx plus c. So now let's say I give you a good old function sine x, okay? Let's say fx equals sine x. Keep in mind this is small fx, okay? So this is what we're going to integrate. So now we can say look something like this, okay? Right? Now let's say we split this axis into say 1, 2, 3, and 4 parts, okay? And now what we do is we draw lines connecting it to the nearest point on the fx. So it should look something like this. Bear in mind that this, and this are all the same. And let's say we call it delta n. Okay, so this is delta 1, delta 2, delta 3, delta 4. Okay? So now, what is the area of this rectangle? Obviously, we must find the height, right? What is the height in this case? Well, it is just f of delta 1, right? Similarly, if I were to find the area of this rectangle, it is delta 2 times f of delta 2, right? So now I can continue and find the area under each of these rectangles. So by this theory, we know that the sum of all these rectangles is just delta 1 times f of delta 1 times delta 1 plus f of delta 2 times delta 3, so delta 2 plus f of delta 3 times delta 3 plus f of delta 4 times delta 3. This is this rectangle. This represents this rectangle, right? Makes sense, right? This is the sum of all the rectangles under this curve. But the problem is that this sum of all these rectangles do not really match the area under the graph, right? Make sense? So now I will use a formal definition, summation, right? So this is known as the summation of n equal to 1 to 5 of f of delta n times delta n. It's just a way to express this. Oh, sorry, it's not 5, it's 4. Right? This is just a way to express the summation of all 4 rectangles. So obviously we would want to increase this value, right? What if this was, say, 10, right? Let's try it. Let's say I integrate this. This is the function. Oh, never mind. That's very bad. Okay. So now I'm going to split this into 10 parts. 1, 2, 3, 6. Okay, let's say it's 6 parts. Okay, not 10. 10 would be very hard to write. Let's say it was 6 parts instead. Right? So now I'm going to draw the rectangles. What do you notice? What do you see? You notice that the area, the sum of all the rectangles that I've just drawn start to match the area under the graph. It's not that accurate yet, but you do see that it looks quite similar, right? It's not exactly the same, but it starts to match, right? Now here, this is, well, 1, 2, 3, 4, 5, 6, 7 rectangles, right? I put 7 rectangles. So now, the area under this graph, the area of the sum of all these rectangles is from n equal to 1 to 7 this time, right? So f of delta n times delta n. If it's still hard for you to understand, you can see this as f of delta 1 times delta 1 plus f of delta 2 times delta 2 all the way to f of delta 7 times delta 7. So now imagine that this 7 approaches infinity. Okay, bear in mind that these delta n's that we are finding approaches 0, right? Because this delta n stays within the same bounds, right? And say this bound is a and b. Between this bounds a and b, when we decrease the value of delta n, and we increase, this is the value, okay, the value, and we increase the number of delta n's. Okay, so what we're doing basically is bringing the number of rectangles to infinity. Now there are infinite number of rectangles. Why? Because there is infinite number of delta n's. But the value of each delta n approaches 0, right? Because they're so tiny. It's probably like 0.00001, right? And you know that it starts to resemble the graph, the area under the graph, right? So formally, what we can say is that the area under a graph fx, it just happens to be the sum of n equal to 1 to infinity of f delta n times delta n. Okay, the problem is that when we do this improper summation, we must express it in terms of limits. So this is the same thing as the limit of, say, j approaching infinity of the sum of n equal to 1 to j of f delta n times delta n. Bear in mind that this is literally the same thing as this, okay? It's just that we're letting this j, this top value, approach infinity, and it's just a method to express it, okay? So now you notice that as j, which is the total number of rectangles approach infinity, the delta n approaches 0, right? Is something we call infinitesimal. It's basically a very, very small value as close to 0, right? And remember, this is in the same bounds a to b. So the number of rectangles become like tiny slits. So slowly, when we increase the value, the graph starts to look like this. And all these lines you see are all tiny rectangles which have a width of delta n and height of f delta n. And you know that this delta n is approaching 0, right? So this approaches 0 and this approaches, well, it doesn't approach anything, but the number of rectangles it approaches infinity in the same bounds a to b, right? Thus, we can say that the integral in this case represents the area under the graph of the bounds. This time we are putting bound b to a, right? So on the intervals of a to b is b to a, okay, of fx dx. In this case, fx is well sine, right? Sine x. This is the same thing as the limit of j approaching infinity of the sum of rectangles, from n equal to 1 to j of f of delta n times delta n, right? Why does this make sense? Since fx represents the height, right? Fx represents the height. And dx, what is dx? Dx is actually just delta n. It's just a notation, because when delta n approaches 0, dx is basically a tiny change in x, right? That's what delta n is. It's a tiny change in x that approaches 0, and that's what dx does. So what do you see? Integral is just the sum of thousands and thousands and millions of rectangles, right, of height fx and width dx from the bounds a to b. So in this case, it has a finite value, right? It has a finite value. And this time, there's no arbitrary constant like c, right? This is the intuition behind definite integrals. This is what we call definite integrals. Hope you enjoyed this video and you finally understand what integration actually is. Hope you enjoy. Thank you.